Hi, I'm Luke McKinney, Prep 101's ENGSCI 1022 instructor, and in this video we'll be covering moments, another core concept that will be contributing to every problem through the course, and a few ways of dealing with them.
In this primer, we're looking at two-dimensional moments, and our first question is, of course, what is a moment? Well, let's have a look at a situation. Let's say we've got a tall tower, and at the top we have a 500 Newton force to the right, and at the bottom we have a 500 Newton force to the left. And looking at the force equations, the sum of all the horizontal forces is plus 500 to the right at the top, minus 500 to the left at the bottom is equal to 0. And that's a condition for equilibrium. So we think, oh, this tower is lovely and safe, but obviously it's not. It's going to do a whole forward flip, which will put you on the cover of engineering textbooks for the next 10 years, but I assure you, you won't enjoy it. So there must be something else going on, something that cares about where the force is applied on here. And that is where we deal with moments, which in some cases, or by some people, are called torques. Now, what is a moment? Well, just like a force will give something a linear acceleration, causing something to move, a moment will give something an angular acceleration, causing it to change its rotational velocity. And that's what moments do. And of course, in Civ 100, they don't do it at all because this must be 0, just like the forces must be 0 for equilibrium. And we're going to write those again because these two equations are the core of almost all the questions of everything here. So we do that. The sum of the forces is 0 and the sum of the moments is 0. Everything adds up to 0. Pretty depressing sounding lesson for first year engineering, but extremely accurate and very useful. So if we know the moments must add up to 0, we better know how to calculate them or what they are. And there's a few different ways we can get a moment. The first is, if I have a beam, I can just put a moment on it. I can say I'm grabbing this and twisting it by 500 Newton meters, which is the unit of moment. Or if I had a beam, I could put a force couple on it, which means I've got a force of 50 newtons up and an equal and opposite force of 50 newtons down. And those are separated by 10 meters. Now, if you have a force couple like this, you can see that'll have the same effect. It'll cause the whole thing to feel a moment counterclockwise. And you can calculate this moment. It's the force, that's just one of the forces, times the distance between them. But what if you don't have a nice exact equal pair of forces? Because you usually don't. Well, we can still calculate those, and we use this every day to get in and out. If we open a door with a hinge at A, if we apply a force, a distance d, away from the pivot, the hinge of the door, then the moment is the force times the perpendicular distance. Now notice something important there. We had a specified point here. So we have to be alert to that. This is the moment around a point. A is equal to the force times the perpendicular distance from that force. So that's perpendicular because that's the shortest possible distance. So now you've got the moment around A is the force times the distance. And from that you can see why door handles are on the outer edge of the door. Because now, for whatever force I apply, I've got the maximum possible distance. So I've got the maximum possible moment around the hinge, giving me the best chance of opening this door. What if I don't have a perpendicular force? Well, don't worry. You're being less efficient, but you'll still do it. And trust me, in engineering, doing things less efficiently, but still getting them done is a big part of the program. So we have a force applied at some angle to the beam, a distance or from the pivot. Again, it very much matters what pivot you've chosen. And in this case, the moment around A is the distance times the force times the sine of the angle between them. And it doesn't matter which of those angles you take because the sine function can handle this. And that's all you need there. If you want to know, these are actually the same force. The same equation. You don't really need to know this next bit, but some people find it useful to help them remember. If you complete this line on and find the perpendicular distance, well, that is the hypotenuse or times the sine of this angle, which is the opposite angle here, which is theta. So we see the perpendicular distance is the distance from the pivot times the sine of the angle. So those are both the same equation. And these equations give us something very useful. Notice in both cases, the moment depends on the distance from the pivot. And that gives us a very powerful tool in solving a lot of problems. We look at it here. If we have our pivot point and our nice door, if we apply another force at the pivot point, now the moment around A is the force times the perpendicular distance, but the distance is 0. So the moment is 0 Newton meters. It doesn't cause any acceleration around that pivot point. And this is true for any force which is applied in line with the pivot. It doesn't have to be exactly on the pivot as long as it's in line with the pivot. For all of these, the moment around A is 0. And we'll use that a lot when we're solving problems. You choose your pivot point to get rid of a lot of unknown forces. Other things about these moments, we can see where the units come from now. The moment is the force times the perpendicular distance. So the units are Newton meters. And there's a convention for the sign. Just like by convention, x is positive to the right and y is positive up. The convention is that moment is positive counterclockwise. Of course, there are ways of doing that the other way around, just like you can redefine the x or y axes. Now, as long as you keep everything consistent, you're fine, but you're best off just using the same convention as everyone else to make your life simpler. Working out 2D moments, but I wanted to show you a fun little example of something that can come up on a problem and an easier way to do it. We're asked here, what is the moment of the 40 Newton of force about A? And we think, no problem, I know how to do that. The moment is the force times the perpendicular distance. So I've got my 40 Newton force, I find my perpendicular distance D, and then I go, ugh, oh no. That'd be a load of trigonometry. I'd have to do triangles and sines and cosines. Like I could work out that perpendicular distance D, but it's a real pain and I'd rather not. And that is a good instinct as an engineer. If there's something that would take ages, you might have to do it, but before you dive in, just check, see, is there an easier way to do it instead? I go, aha, I have another formula I could use. It's the distance times the force times the sine of the angle. And you go, oh no, because that is even worse. I'd have to calculate more distances and angles. Or I could extend this line and find this distance and this angle instead. Again, all things we could do if we sit and plugged at it for a while, but we'd rather do it smarter and easier. So what you do instead to do this sort of problem faster is if you have an angled force off at some awkward location, you just break it up into horizontal and vertical components. So the horizontal component is 40 times cosine of 30, which is 34.641 newtons. And in y, we have 40 of sine 30, which is 20 newtons, to the same degree of precision. So then we draw that. Bing! There it is, the magics of technology. But I wanted to show, remember to draw your own axes so you remember which way is positive and negative. So now the moments around A of these two forces are, you have 20 newtons, a perpendicular distance of 4 away, and that's turning counterclockwise around A, so that's positive. And then you have 34.641, a perpendicular distance of 2 away. And again, that would turn things counterclockwise around A, so that's positive, which gives us 149.282 down to 5 sig fig for my work, down to 3 sig fig for a final answer, 149 Newton meters. You see, in each case, the work gets handier. You break it up to one step at a time and just plug through it. But when you see something that looks like it's going to be 4 or 5 steps, well, just back off a little, see if there's a way of doing it in 2 steps instead. Let's look at calculating a moments, because there's a couple of common little misconceptions or mistakes I've seen people make. So I wanted to do a little example. We've got a beam here pinned at A, and at the pin you have 2 unknown reaction forces, a horizontal and a vertical. You actually have this at any pin or hinge, and we'll see a bit more about that in the support reactions primer. We got a 20 Newton force down 2 meters away, 100 Newton meter clockwise moment 3 meters away, and an unknown force F 5 meters away. And we're asked what force F is required to hold this beam motionless. So we're being asked what will hold this beam in equilibrium. The sum of the forces is 0 and the sum of the moments is 0. Well, the very first thing we do is we add an axis to make sure we get everything the right way around. So X and Y are positive, right and up, and the moment is positive counterclockwise. Now here's a little trick. You might have learned the forces first, but for any problem, you do the moments first. It'll be faster, you'll find a value sooner. It might be the value you need right away, and even if it isn't, it'll help you work things out a lot faster. So we take the moments first. And we know if we're calculating the moments, we have to calculate around a pivot point. What pivot point? Well, we always choose the pivot with the most unknowns. Because remember, any unknown acting through the pivot produces 0 moment, so it disappears from our equation. Well, we have 2 candidate points. A has 2 unknowns, and this point over here has 1 unknown. In fact, it actually has 2 because AX goes right through it. So we're okay with either of those. So for convenience, we'll take the pivot point as the hinge at A. Usually, if you have a nice single hinge like that, or a ball and socket joint in 3D, which you'd look at later in the course, you'd always choose it there. So we take the moments around there. Let's have a look at them. So the sum of the moments is 0, so AX goes right through the pivot, so its moment is 0. AY goes right through the pivot, so its moment is 0. 20 newtons is a perpendicular distance of 2 meters away. Remember, moment is force by perpendicular distance, and that's turning clockwise. But we know counterclockwise is positive, so that's negative. Then we move on. We have 100 Newton meters clockwise, so that's negative. Now notice there's no distance there. We don't care about this distance because this is already a moment. So it doesn't matter where on the beam it is. You don't multiply that by 3 meters, because if I'm grabbing the thing and twisting it, it doesn't matter where I'm grabbing it. That's how much I'm twisting it already. So only forces need distances. So that 100 doesn't have a distance term, while the 20 Newton force does. And then finally, we have the force F 5 meters away. And that's turning counterclockwise around A. So that's positive. And that's all of the things that are acting on the beam. And that all adds up to 0. And now we've got that lovely thing, one equation with one unknown. And we find we have minus 140 plus 5F is 0. So F is 28 newtons. And the sign tells us the direction. Remember, in engineering, plus and minus are just directions. So if it's positive, that means it's in the direction of the arrow for F, which was up. And so we've worked out F. And then if we wanted, we could find the size of AX and AY by doing the force equations next. So we do the sum of all the vertical forces is 0. Let's do horizontal first. Sorry, I was defaulting ahead. My habits, you see, I've done 1,000 of these problems, but the horizontal forces, so we've plus AX to the right, and nothing else is 0. So the horizontal force is 0 newtons. And then the vertical forces is 0. So if we look at it, the arrow of AY is pointing up. So we've plus AY up. Then we had 20 newtons going down. Then we'd plus F, which is 28 going up, which is 0. So we find that AY plus 8 is 0. So AY is minus 8 newtons. That's negative. So it's opposite to the arrow. AY is down. Doesn't mean anything's wrong. You didn't make a mistake with the arrow of AY at the start. It's just an axis like any other. Plus is in the direction of the arrow, and minus is the direction opposite to the arrow.
I hope that was useful. There's plenty more videos in the playlist, but what's even more useful is lots of exam examples and exam specific advice. And that's what we do in the prep sessions. So join the Prep 101 Study Hub Facebook page to find out when those go on, and many of them are even free, so you definitely don't want to miss those. Hope to see you there.